All right, let's talk about the sun. We see it every single day, right? But have you ever stopped to think about what's really going on inside that massive, brilliant ball of light? Well, today we're going to find out. Here's the central question, really. It's a puzzle that's been around for a long, long time. Our sun has been steadily shining for about 4.5 billion years, and it's got at least another 5 billion years left in the tank. So, how is that even possible? What kind of fuel lasts that long?
If your first thought is a giant campfire in the sky, you're not alone. That's actually what scientists used to think too. But the real answer isn't fire at all. It's something way more extreme and a whole lot more powerful.
So, first things first, let's get that big misconception out of the way. Why isn't the sun just on fire like a giant log burning in space? Well, it really just comes down to the math.
Okay, let's dive into this. Way back in the 19th century, scientists did the calculations. They figured out that if the sun was burning through a chemical fire, or even if it was just heating up by shrinking under its own gravity, it would have burned out millions of years ago. But we knew from geology that the Earth was billions of years old. The timelines just didn't add up at all. It was clear that some other, much more powerful process had to be at work.
And that something else is the absolutely incredible engine at the heart of not just our sun, but pretty much every star in the universe: nuclear fusion. This right here is the secret sauce. This is how the sun has such unbelievable stamina. It isn't burning fuel, it's fusing it. And this all comes down to Einstein's classic famous equation, E equals mc squared. It tells us that mass and energy are basically interchangeable. Fusion takes a tiny, tiny amount of mass and converts it into a truly mind-boggling amount of energy. So how does this actually happen in our sun? Well, the main reaction is something called the proton-proton chain. In the absolutely crushing pressure and heat of the core, hydrogen nuclei, which are really just single protons, get slammed together. It's a multi-step dance, but basically 4 protons go in, and after a few steps, 1 stable helium nucleus comes out. And that little bit of mass that gets lost in the process, that's it. That becomes the light and heat that powers our entire solar system. Now, the proton-proton chain isn't the only fusion reaction out there. There's also something called the CNO cycle. This one's a bit different because it uses heavier elements, carbon, nitrogen, and oxygen, as catalysts. Think of them as cosmic matchmakers. They help the reaction happen, but they don't get used up themselves. For stars that are way, way bigger than our sun, this is their main source of power. In our sun, though, it's a minor player, accounting for less than 2% of its energy. All right, to really get a feel for this, we've got to take a journey. Let's go deep inside the sun, right to the spot where all this incredible magic is happening, the core. You can kind of think of the sun like an onion with all these different layers. You've got the outer layers, the convective zone, and then the super dense radiative zone. But all the real action, all of that nuclear fusion, is happening in one very specific, very extreme place. Right at the center, in the core. And the conditions there, they're just hard to even wrap your head around. The temperature hits 15 million degrees Celsius. That's the kind of insane heat you need to get those hydrogen protons moving fast enough to overcome their natural instinct to repel each other and actually smash together. And get this, all of that energy generation, everything we've been talking about, happens only within the inner quarter of the sun's radius. That means less than 2% of the sun's total volume is creating 100% of its power. The energy is just unbelievably concentrated in there. So to put a number on it, every single second, the sun chews through about 600 million tons of hydrogen, fusing it into helium. And in that process, about 4 million tons of that matter is converted directly into pure energy, every single second. That incredible efficiency is what has allowed our star to shine so steadily for billions of years. It's what made life on Earth possible. So, okay, we've created all this energy in the core. But how does it get from that super dense center all the way out into space and eventually to us? Well, this part of the story is one of the most amazing and just plain weird things in all of astrophysics. So a photon, a little particle of light, is born in a fusion reaction. You'd think it would just shoot straight out at the speed of light, right? Nope, not even close. It immediately smacks into a wall of ridiculously dense plasma in the layer just outside the core, the radiative zone. And because of that dense plasma, its journey from the core to the surface is unbelievably long. The energy from that one little photon could take, on average, more than 170,000 years to finally escape the sun. Just let that sink in for a second. The sunlight that's warming your face right now was created back when Neanderthals were still walking the Earth.
So what's taking so long? It's because the photon gets absorbed by an atom and then spit back out in a totally random direction. It zigs, then it zags, then it gets absorbed again. Scientists have this great name for it. They call it a drunken walk. It's this endless millennia-long process of stumbling from atom to atom, just trying to find its way out.
Okay, so we've looked at the sun's ancient past and its brilliant present. But what about the future? What is our star's ultimate fate? Now don't worry, we've got plenty of time. Right now, the sun is a nice, stable, middle-aged star. But in about 5 billion years, it's going to run out of hydrogen fuel in its core. That core will shrink and get hotter, which will cause the outer layers to puff up and expand like crazy. Our sun will become a red giant, swelling up so big it'll probably swallow Mercury, Venus, and maybe even Earth. Then, after all that drama, it'll shut its outer layers, leaving behind just a tiny, super dense core, a white dwarf that will just slowly cool off for trillions of years. So, it's amazing, isn't it? Starting with a simple question, why does the sun shine? We end up uncovering the fundamental laws of the entire cosmos. It's our life-giving furnace. And as we send probes like the Parker Solar Probe to get closer and closer to practically touch the sun, you just have to wonder, what incredible secrets is it going to reveal to us next?